I'll begin. Dearly Father, we thank you for this day. We thank you for the weekend about to start, for the short break. Help us to use it wisely. And again, I just pray that you'd be glorified in what we do this morning, Lord. In your name I pray. Amen. So, any questions about homework? Okay, so the Stokes Theorem is what we're talking about today. And I'm going to start us out with just a small, what does Green's theorem say? Let's just think about that for a minute. What was Green's theorem, the curl form of Green's theorem? We had what, for like, so here was z hat, right? This is r, the boundary of r. And what did we have? It was, the integral of what was it? P dx plus q dy is equal to, what was it, or the boundary of r, double integral of partial q partial x minus partial p partial y dA, right? So my question to you would be, what if instead of this kind of thing, what if we had something like S, and this was, say, y hat, and the boundary of S was oriented like that, So this I'm drawing some sort of disk in the ZX plane, all right? And if we had the integral, let's see here. So again, to try to keep my picture quasi-honest, here's z, here's x. So maybe I could look at something like, I don't know, p dx plus r dz, right? Boundary of S. What would Green's theorem look like in this system of coordinates?
Haphazard guess. Partial r dx minus partial p dz.
Let's see here. So you say it's partial r, partial x minus partial p, partial z. See, I'm not sure.
There's a third coordinate, and this is three-dimensional.
Yeah, but this is in the ZX plane. So
Okay.
here we have y is playing the role
Y is normal to the surface
of z, but actually that's misleading. Here's the way I should really set it up. I should really say the integral over the boundary of S of r dz plus p dx to be fair, because you see up here we have x and we have y, right? And x hat cross y hat is z hat, right? How do I get y hat from x hat and z hat?
z cross x.
Right, z cross x. So I should put the z first and the x second.
That should be
Right, so this is actually going to be partial p partial z minus partial r partial x would be. That would be what Green's theorem looked like. And this dA, to be more sort of, this would be dx dz, But the larger point here is that what this is, in both cases, in this case, we're looking at the integral of f dot dr is over the boundary of r is equal to the integral over r of the curl of f dot z hat dA. And in this one, where f is what? Well, actually, it doesn't matter what f is. And this one down here, we're looking at f dot dr is equal to the integral over s of the curl of f. This is actually the y component of the curl. So I could say y component, or I could say dot y hat, same deal. I mean, if F also had a, if there was also a Z component, like if there was an R component in the first one, or if there was a Q component, so to speak, in the second one, it wouldn't change these as it happens. So if you look at Green's theorem, you can see evidence that there's some deeper theorem here about the curl. That's Stokes' theorem.
Came after Green's theorem?
They came after Green's theorem? Historically, I don't know, actually.
Well, because I mean, if Green's theorem is just a smaller subset of Stokes' theorem, and Stokes' theorem existed all the while, Green would never have gotten credit for it.
I just don't know the history of it. But, yeah. Can you flip the lights? Like, yeah, there we go. So here's Stokes' theorem. So the way I say it in the notes is a little bit different. My basic point here is that if you can derive Green's theorem for the xy plane, you can just as well derive it for any plane. So like down here, so if S is some area in a plane with normal n hat, then Green's theorem applied to that plane says that the integral of a vector field around a curve in the plane, which has boundary S, is just given by the normal component to the plane of the curl integrated over the area. And I've illustrated this idea for you over here by looking at a ZX plane, right? So my next move is to say, okay, well, we can do this for a surface, but a special kind of surface, just to be logically precise, if I take a surface called a polyhedra, it's formed from the union of finitely many polygonal faces, like this. I'm not saying it's closed. It's got an edge down here, so to speak, right? And on each one of these faces, I can apply my Green's theorem, right? And so if you apply Green's theorem to each face, and then you just add it together, we get what's called Stokes' theorem. At least for the simple, I call this the baby Stokes theorem because, of course, regular surfaces don't look like this, right? Like regular surfaces are not polyhedra, they're something else, right?
I suppose have them as polyhedral.
Well, that's where we're going. That's where we're going. Yeah. So basically, what I'm going to do is I apply Green's theorem to each face. For each face of the polyhedra, I have that the integral around the boundary of the face is the area integral of the curl over the face, the surface integral. So I calculate the flux of the curl through each face, and then I just add these together over the faces, right? So what happens as you add these integrals over the face here? If you add together the integral of the curl over each face, you get the integral of the curl over the whole thing, right? Because when we add integrals, we just union the surfaces we're integrating over, right? So this just adds together as I add them up. On the other hand, this is more interesting. What happens as I add the line integrals? Well, look at these. So like the integral over the boundary of 1 and the integral of the boundary of 2, there's some cancellation that's going to happen. As I calculate the line integral of f over this one and that one, these cross-cuts cancel out, right? And we're left with like this piece and that piece. Then as I add S3, I cancel out the other side of S2, right? As I add in S4, these two line integrals cancel. As I add in I can't read my writing, 5, these cross-cants cancel between 2 and 5 and so forth, right? And if you think about this, the only edges which don't cancel are the ones which are truly boundary to S, right? Any interior edge between the faces of the polyhedra, they cancel out because of the oriented nature of the line integral. And so here's the equation. So I'm saying sum over the faces, the line integral, sum over the faces, the flux integral. So this one is just the total integral of the curl over the surface, like I said. And then this one, if you add over the boundaries of each of the faces, it ends up just being the total boundary of S, the oriented boundary of the polyhedra. And that's Stokes' theorem. Now, but again, this is for a special thing, for actually polyhedra, right? And then what Thomas has said is actually my idea. If you take an arbitrary surface, right, you can imagine better and better and better and better approximations to the surface using polyhedra as an approximate for the surface, right? I mean, video games are built over stuff like this, right? You don't, if you have some curved surface, you could use some sort of like interpolating polygon, something like that. And if you choose it finely enough, it looks like it's, I mean, you can't tell the difference between curved and not curved, right? So that's the idea, is just take an approximate polyhedra for the surface and take the limit as the number of polygonal faces goes to infinity. And at each stage in this limiting process, we can apply baby Stokes theorem. And then passing to the limit, we get Stokes theorem. Now, this is not a limit I'm going to explain in here, but I do believe intuitively, at least, that argument makes sense. Now, in terms of mathematical rigor, that argument lacks something. But a little bit later in this section, I give a proof of Stokes theorem for a graph. And that theorem's pretty rigorous, and it uses the fundamental theorem of calculus and all that good stuff. So I don't want to do that right now. What I want to do now is just show you how to apply Stokes theorem to a couple simple examples. Yeah. Before I do that, though, and while I have this out, are there any questions about your homework? Because I can look at the problem statements with this out, and you guys, yeah. Which homework are we on? I got so many different classes, I've lost track of where I am in which class, and it's just, this time of the semester is just crazy. So 13? Okay.
So on 160,
Let me just,
divided the oriented curve.
counterclockwise oriented curve. This is a ellipse, right?
Yeah, so I divided by 360, and I graphed it. So, like, would the bounds be -2 to 2 and -3 to 3?
No, that would be a rectangle. Right. You can hit the lights, Dustin, if you don't mind. So let me so you divide it by 36, and you got x squared over. Okay, great. Equals to 1, right? And so that's an ellipse. Let's see, we've got x-intercepts of plus or minus 2, y-intercepts of plus or minus 3, right? So it's something like this. Badly drawn. So what you want to, so you're trying to calculate the integral of partial q partial x minus partial p partial y over this area, right? And the question then really is how, right? Now if you use Cartesian coordinates, the answer is this. So this is 2, this is minus 2, and we have minus 2 less than or equal to x less than or equal to 2, and we have minus the square root of, let's see, solve this for y. 3, y is equal to plus or minus 3 square root of 1 minus x squared over 4, yeah? So we'd have minus 3. Now, I don't recommend you actually do this. I'm just saying if you were to use Cartesian coordinates, this is what it would look like.
But you should use elliptical coordinates.
Yeah, my suggestion here would be to trade these for making, like, I would rather work with x over 2 equals to u and y over 3 equals to v, because in these coordinates I have u squared plus v squared less than or equal to 1, and then I can use polar coordinates in uv, like the uv polar coordinates, to do the integrals the best way.
Okay. Just like we did in a previous problem, right, where we showed how that's
So basically this is the integral over the ellipse. It's not really, it's the integral over the interior, I mean the solid ellipse. I don't know what to call this. Elliptical disk, there we go. Ellipse. Elliptical disk is a good term, yes, okay. And you can tell me what partial q, let me just put what in that is just to be a little bit less, what we got here. Partial q partial x is 2, And that's what? So we get what? 2 minus 1?
Yeah.
Oh. So this, ironically enough, is 1. So this is actually the question. This is just a really weird way of asking what's the area of an ellipse, right? But yeah, so my next move would be, this is u squared plus v squared less than or equal to 1. The reason I wanted to do the derivative here was because if there had been an x and y appearing here, I would have needed the expression, because then I would have had to convert it to the uv stuff. But that's kind of boring here. So I have, what's the Jacobian? Right. Which then I would convert to, so what is that? That's 6, yeah? So then I would say, well, that's 6 times the integral from 0 to 2 pi. I'm sorry, I seem to be working the problem for you. My apologies. R dr d theta, where I'm introducing polar coordinates in the UV plane, right? So like here, u is equal to r cosine theta, v is equal to r sine theta to make, we can make a polar substitution past the UV substitution. Because again, I don't really want to do the integral over a disk in Cartesians, even if I'm calling the Cartesians u and v. So, or at that point, you can say, well, it's a unit. It's 6 times the area of a unit circle, and I already know that the area of a unit disk is pi. So, I don't know. At some point here, you can refer to a known result. Does that make sense? Yeah.
Well, presumably, once we got to dq, dp, dA, and then we realized it went to 1, we just go, oh, it's the area of the ellipse. But I have a feeling you want us to use calculus.
Well, yeah, even so, for this problem, you should derive the area of an ellipse, I think. We have done it before, but at a minimum, you should say, in problem such and so forth, we derived the area of an ellipse was blah, 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 at a minimum, right? But now, in contrast, actually working out this line integral directly seems more daunting, right? I'd have to parameterize the ellipse, and then you've got 3, whatever it is, whatever the x formula is. I guess x is 2 cosine theta, and y is 3 sine theta. So you'd have 3 times 4 cosine squared, and there you have a 3 sine theta. Your dx would be, it would look at least a little bit scary to start with in the line integral. Of course, most of those things go to 0. Other questions? That's a good question. Sorry, I told you too much about it. You'll forgive me. Yeah.
163.
So let's see here. Let's C be a piecewise smooth curve. Piecewise smooth curve, closed curve. What? Too many curves. Piecewise smooth closed curve. Get rid of one of these curves. I don't know. Which encloses a simply connected region with area A. Suppose A, B, C, and D are constant. Let's calculate this thing. So let's see here. Integral of C, AY plus B, dx plus CX plus D. I'll try not to work the problem for you. dy. It's hard for me though here. This is P. This is Q. And what did I give the name region? Oh, A. So the picture is something like this. Here's A. The boundary of A is what I've called C, right? So Green's theorem says what? This is the double integral over the area of partial Q, partial X minus partial P, partial Y. I mustn't write any more. So you should apply Green's theorem. It should, and I think the partial derivatives here work out to constants, so it should just give you some kind of A, B, C, D, and you should be able to, the answer should be in terms of A, B, C, and D possibly, and the area of A, whatever that is.
Does connected region or a piecewise smooth curve, that doesn't help you at all with the bounds of integration.
It's an arbitrary reason.
Oh, okay.
Yes, if I wanted to make this problem, if I wanted to be mean, right, I would actually give you a specific area to work this on. You know? Then you'd be distracted by the details of how you set up the area. But that's not at all the point here.
Well, yeah, but I'm distracted by the lack of details.
Nah, don't be distracted. Other questions, yeah?
I'm still
Mhm.
completely lost as to how you go
Is there a
past
specific
the
problem,
setup.
I guess, just for me to understand the wording better, does, like, outward-oriented graphs depend if we're gonna find outward flux?
Which problem are we talking about?
Take the question.
Or just generally?
Well, like, just in general, because I know we've done examples where it's not an outward-oriented
You just
curve,
read it as an
but we
integral.
found, like, normal flux, or, like, it's.
So,
Like, I just understand the correlation
Oh.
between oriented curves and normal flux, or
okay.
outward flux.
I think I understand the question. There's the two-dimensional question and there's a three-dimensional question, right? So for the two-dimensional flux, we proved the other day that the integral of, oh man, I never remember this stupid thing. I think it's q dx minus p dy. 50-50, I'm right or wrong.
I think it's something like that.
Yes.
Yes, p dy minus q dx. I chose poorly. So what this does is this calculates the flux. So you got some C, right? This calculates the flux in this direction. I'm drawing positive field streamlines, assuming that this is counterclockwise oriented. I mean, this is a line integral. I mean, so of course you can understand flux through a curve without, whether it's clockwise or counterclockwise, doesn't matter really. In principle, you understand it's going out of the curve, right? But this line integral needs an orientation. And we derived that that was equal to the integral of the divergence, right? As it happens, the two-dimensional divergence over the whatever region this is that's bounding, right? So whenever I'm asking a question about flux through a curve in the plane, we need to keep this in mind. We should think about the line integral with respect to a counterclockwise curve if we're going to use this theorem. But I don't know did I say like the integral? I may have said the integral, the flux through a curve in the plane, assuming that the curve is counterclockwise oriented. If I do such a thing, it's just to try to remind you that we have to do this counterclockwise. But I don't know. From geometric perspective, I'd rather I didn't say that. I think if I have said that, I think I was trying to point you towards this. This is how we calculate flux in the plane. Now, surfaces. Let's talk about surfaces. A graph doesn't have to be closed, so outward doesn't make sense, right? For a graph, to calculate the flux through a graph, I need to give you a sense of which way's up. So here's, for example, we could ask, we could say the vector field f, x, 0, 0, for example, and, well, yeah, sure, x, 0, 0, nah, but I'll make up my mind here in a second. 0, x squared, 0, like that. So this is a vector field, and I could say, what's the flux through the graph? Graphs could be z equals f of x, y, but another kind of graph would be y equals to, we could look at something like y equals x squared. And so just to draw a picture of that, y equals x squared. If this is y, this is x, this is y, right? So y equals x squared in the xy plane looks like this, so to speak, right? But it's like that at every level, you know? So this actually gives us a cylinder. Badly drawn cylinder. I mean, it's a parabolic cylinder. We get one of these at each z, right? So if I ask you what's the flux of this vector field through that surface, let's say for 0 less than or equal to z less than or equal to 1, and for 0 less than or equal to x less than or equal to 1, just to make it, you know, a reasonable question. Now, this describes the surface, but I haven't told you which way's up yet. So I'd have to add wording like, say, oriented such that oriented in the y-hat direction, for example. You know. Now, so once I say that, oriented in the y-hat direction, find the flux of f through that, then that's a meaningful question. Now I'd have to figure out what's a parameterization of the surface which puts the normal on that side, and go from there. Now I could just work geometrically, right? Like I think it's fairly clear here that the ds hat, we could use what? We could use like, well, I should be careful. Do you want me to work out that problem? I mean, I could work out this problem. Would it be helpful? It might be helpful for me to work this out. We haven't worked one quite like this, have we? I guess we have.
Yeah, because this one doesn't end up being 0.
This one doesn't end up being 0? All right. I deserve that. Let's see here. So first order of business, we had to parameterize this thing, right? So let me suggest that we do x, and I suggest we use, if you think about a point on here, any point on this surface is uniquely given by what? X and z. So x and z are nice choices, right? Now if you think about z crossed into x, it goes in the y-hat direction. So I'm just intuitively guessing that I should do zx here to put the normal on the side I want it to be. Now what's the formula for the x component if I use z and x as parameters?
I mean, don't you want to put the z component first? Or does it not matter?
This is the parameterization. I have to put x, y, z.
Oh, okay. So
This is not complicated, folks. X, yeah. And then y requires some thinking. Z is again like that. Now, the surface is described by y equals x squared. So what do I put for y? X squared, right. And again, this is for 0 less than or equal to x comma z less than or equal to 1. So then I calculate my normal, which would be partial x, partial z, cross partial x, partial x. This is technically a graph, all right? Anytime you write the third Cartesian variable in terms of the other two, that's what's called a graph. But this isn't the standard graph, right? Like a standard graph is z is a function of x and y, right? So being that it's not the standard graph, I kind of have to work this out because I don't have it just like if we had z equals f of x, y, we could go back to my like number 4 or 5 on my list and copy the normal down from there. Here I have to work it out, which isn't a bad thing. 0, 0, 1 crossed with 1, 2x, 0. Now this one, you should not use determinant for. This one you should use good old-fashioned algebra. This is z hat crossed with x hat plus 2xy hat. What's z hat cross x hat? So this gives us y hat plus 2x. What's z hat cross y hat? Minus x hat. Or, in other words, this is minus 2x, comma 1, comma 0. Now, as a check, you should check that the normal vector field is actually perpendicular to both of the partial velocities. Is it? Perpendicular to 0, 0, 1. Good. The dot product of 1, 2x, 0 with minus 2x, 1, 0 is also 0. That's a good check if we calculated the cross product correctly. So there you go. That's my normal vector field. So that says that ds vector is minus 2x, comma 1, comma 0. And here we're using dz dx, right? So to calculate the flux, over this. I never gave this thing a name. I will name it Herbert. So the integral of the flux over Herbert, flux of f through Herbert, oriented in the y-hat direction, obviously.
The thinking of your Herbert on isn't actually part of the derivative, because you said 0 is less than equal to x less than equal to 1, right?
That's okay. We don't have to take the flux over as neat.
No, fine, I'll behave. Sam got me. Yeah, this isn't really, it's like kind of a, I can't draw it worth anything with my current choice of orientation. But I mean, it looks like this from the top view. And the y-hat is like this. Anyway, bad pictures aside, what is the integral here? We're integrating from 0 to 1. Integrating from 0 to 1. What's f? F of, my f was 0, x squared 0, which is actually 0, x squared 0. Sorry, this one's not very exciting in terms of, like, evaluating f at the parameterization here is kind of a non-event since we're using x as a parameter. Putting the vector field in terms of x equal to x, it's like, yeah, okay. And then dot with, I really hope this isn't 0. That would be nice. Okay. But this is also actually not too bad a problem. This is actually a pretty nice test question, don't you think? I mean, to make a decent test question. This is just x squared dz dx.
There's 1/3.
So yeah. So we can factor the integrals because they're not intertwined. Let's see here, dz, which is 1/3 times 1. So yeah, the flux is 1/3. But getting back to your original question, like, I would say if I just say the outward-oriented graph, I don't think that makes sense. If I say it's an upward-oriented graph, if it's like z equals f of xy upward, we usually just take, it's a considered standard nomenclature to take positive z direction is up, right? Or if we're working in, well, yeah. So, but now if it's like a sphere, outward-oriented means that the normal's on the outside. Inward-oriented, the opposite. But if you're ever not sure about which orientation I intend, you should just ask me, because it shouldn't, that shouldn't be a ambiguous thing for a problem that you're given. Yeah. Although there is a way to make it ambiguous. See what we could do is we take this, like this, stealing my thunder. Let's see here, and then just, I should have made it narrower. Just twist like so. And then this is the example of a non-orientable surface. See, if I start on one side here, and I go around it like this, and then I end up right back where I left. This is a one-sided surface. You can't pick a non-vanishing normal vector field on this thing. So describing flux through something like this, it's not quite possible with our current definition. But there are ways of integrating over this, but that's not a usual topic in Calculus 3. So this is, we always calculate flux over oriented surfaces. Or, of course, if I was just to focus on a little patch here, I could still calculate the flux through a given patch of the Mobius strip, supposing I told you which way was up on it.
So we selectively pick your patches and then.
Yeah, but that'd be pretty ad hoc though, right?
Yeah, but it still vanishes if you try to do that. So.
Any questions? All right, let me do some examples of Stokes theorem then. Oh, by the way, at this point, you have seen all the major theorems of Calculus 3. Like we talked about I mean, you've seen Boo. I mean, I have a few more to add, but these are the ones that are supposed to be tested in Calculus 3. Well, in the universe of Calculus 3 instructors, there's something like a 60% chance across all universities that the divergence in Stokes theorem won't be covered in your course, which is a dirty, rotten shame because it's the whole point of the course. Sorry, but this is how I feel about it.
So Stokes theorem is the ground rule.
Well, I don't know if Stokes theorem, to me Stokes theorem is a weirdity. The divergence theorem is the one that's really, really nice. Yeah. Yes. That's awful. Yes, we should be stoked for the divergence theorem. That's truly an awful comment, but I'll allow it. Here we go. F equals to minus yxz. And we want to find the flux of F over half of the outward oriented sphere. So I guess here's a slight twist on what I was just telling you, Emma. I mean, this is not a closed surface, right? But if we completed the half orient, I mean, it's just half of it, right? But it's part of something that's closed, so there's still a sense of like what's outward.
Which half?
I'm not done. Rho equals to r with z greater than or equal to 0. So here's a picture. So we're looking at the normal like this. Right? And so Stokes' theorem says, something call this thing r, that the integral of the curl of f over r is equal to the integral of the line integral of f over the boundary of r. This is what Stokes' theorem says. Now that has to be the consistently oriented boundary, okay? So what that means is if you imagine yourself a little dude, or dudette, I mean, whatever. At least I don't want to get into any Title IX trouble here. Let's see your, so imagine yourself walking along. The surface should be on your left, right? So that means it's like this, right? It's the Vine Center, yeah. Sure, why not? Now, what is this? This is what? This is the sort of the equator, or the equatorial great circle. This is z equals to 0, and x squared plus y squared equals to r squared. Hey! Sorry. I didn't hear me. So to calculate the line integral, we should parameterize this circle. Can you do that? 0 to 2 pi f of, what's the parameterization of the circle? How about r cosine t, r sine t, 0. And then I have to dot with the velocity vector here, which is what? Minus r sine t, r cosine t, 0, dt. Which is what? Let's see, f, I do what? Minus y goes in the first thing, so I got minus r sine t. Welcome back. Let's see here. And then x is r cosine t. And then z, oh, z I like. Z is 0, although it really wouldn't. Oh man, this is boring. Look what happens here. Don't worry, it's not 0. It's not 0. That's not what I was saying. Not that kind of boring. Not that kind of boring. Don't get ahead of me. This problem's on the homework. This exact problem's on the homework. What? It's almost like I'm giving you a reward for coming today and or paying attention to the lecture right before Easter break. So there you go. It's also in the notes, yeah. Well,
Down to R.
so if it's in the notes, if it's on the homework, right, it must be on the test, right? Yeah, okay. That's not a promise. It's just a, you know, a possible, I mean, I am a creature of habit, right? So I would say the odds of this example being on the test are higher than certain other examples, right?
Although, if you're giving us half of the outward oriented sphere, you should make it more interesting on like x is greater than 0 or something. That way it's slightly different.
Well, I could ask the much more annoying verify Stokes theorem on the outward oriented half sphere. This is only half of verifying Stokes theorem. Verifying Stokes theorem means calculate the curl, calculate its flux, and calculate the line integral, show that they match. That wouldn't be hard here. What's the curl of f? You know what? I'm not going to do that. Let's go on here. I want to, if I do that, it's hard for you guys to appreciate. I mean, if I verify everything in the theorem, it gives you the impression that the theorem is harder than it actually is. This is the point. So let me not do that at the moment.
So the goal of the theorem is that you don't have to verify it.
Precisely. Yes. Yes. Another example. This is kind of a meta example. Is suppose you have a closed surface. And you have a vector field which is nice along the surface, all right? I mean, technically, the thing I haven't emphasized, but it is important, is that in order to apply the Stokes theorem or the Green's theorem, any of these things, you're taking derivatives of the vector field, right? And then you're integrating. So you do need that the derivatives of the vector field exist and that they're nice enough to integrate. These kinds of mathematical preconditions I have been a little bit sloppy on in here. Sorry about that. So example 2, suppose you have a closed surface, say a sphere, and you want to calculate the flux of the curl of a vector field through this sphere. What is it? It is 0. There is no boundary, right? But let's verify it through less elegant applications of Stokes theorem. I mean, we can break this into two pieces, right? S north, S south, right? So this would, right. So the north piece of the curl of the north through the north face plus, I mean, this is, in some sense, this derives what you just said. For surfaces without a boundary, in fact, Stokes' theorem says that the integral around the boundary is 0, yeah? I mean, but that doesn't seem to say anything because there is no boundary. Well, anyway, it says what we can say is that the flux of the curl over a closed surface is 0, right? So the point here then is, so ds looks like this down here, right? ds looks like this up here, right? Outward oriented. So if we think about the boundary, think about yourself, little dude, you know, walking like that, then this is the boundary of S north, right? But the southern boundary, up is down and down is up, right? So down there, if I can find we say the Australian boundary. Say, yeah, sorry. So down here, yeah. I should really have reversed the color coding given the politics here, but let's see your partial.
I mean, you could use orange instead of
S.
Then it would just be mathematical.
I mean, at least in the American South, you
And the point here is that these cancel because this is equal to minus the boundary. They're the same point set they just had. They were just the reversal, right? The boundary of the northern part of the sphere goes around like that, right? The edge of the southern hemisphere goes the other way. So if you want, I can draw this picture again. It may be helpful to sort of separate it like this. Just kind of draw a little gap in. So this one, around the top, the orientation's like that. On the edge down here, the orientation's the other way. You put them together. Yeah. So, 0. I don't think this is the easiest way to show that either, by the way, guys. There's another way to do this one. Since I already spilled the beans and told you guys the divergence theorem by accident the other day, after my unfortunate too many zeros, here's the alternate way to solve this problem, which I much prefer, actually. So if you take the integral over the surface, which is the boundary of some volume B, let's say, then applying the divergence theorem, which we haven't proved yet, or even stated very carefully, sorry about that, I'll get to it after break, then this is the integral over the solid region of the divergence of the vector field. But what's the vector field here we're looking at is a curl. And by the way, what did we prove back when we were talking about curl and divergence? Remember, we proved the gradient of the curl of a gradient was 0, and we also proved, or I should have proved, or you should prove. Anyway, it is known that the divergence of a curl is also 0.
Okay, so when S is a surface and you write partial S, then that means a curve, and when B is a volume and you write partial B, then you get a surface?
Well, S is a surface, so if B is a volume, then the boundary of a volume is a surface, yeah. The boundary is always like a one less dimensional thing. So anyway, integral is 0. 0.
What's the boundary of the point?
Well, that's an interesting question. If I have a curve like this going from P to Q, and this is a curve, then the boundary of C is the 2 points. Yeah, it's P and then Q.
So it's the boundary of the point.
Boundary of point is empty set. And, yeah, it's got there's no boundary. Yeah. Let's see here.
So wait.
Second, guys. So I have, in terms of flux integrals, I have like 3 or 4 more in the notes I haven't covered yet that are nice. In terms of examples of Stokes theorem, I have, that's a good example. I mean, past that, next time we'll talk about Stokes theorem with holes and the divergence theorem most likely. And I'll cover the proof over a graph for Stokes theorem on Tuesday, most likely. So that's where we're going. Have a good break.